Okay, in this question, the quarter circular cantilever beam. So we have a beam here. When you hear the word beam, it means that here we have a reaction moment and reaction force in x and y directions. So we don't have xy coordinates, but I'm pretty sure you know where are they. We have a uniform pressure on its upper surface. So we have two surfaces. One surface here is the bottom part, and this part is the top surface or upper surface. The pressure is expressed in terms of the force P per unit length. So pressure, what is the unit for pressure? It is Newton per meter squared. But here it says in terms of the force P, it means that Newton per meter, because it's length of circumferential arc. Determine the reactions on the beam at its support A. So here we have just one support A. In terms of the compression CA, shear VA, and bending moment MA. So we have a moment MA and CA and VA. Okay, let us solve the questions. First, you need to find an element that the pressure is applied to it. Any element, any arbitrary elements. So I will just show you here. I will choose these elements. I will make it bigger here for you. This ones. This is these elements. Okay. So, but I will just show you how much is the length of this part first. So how much is this length? We know that this radius is r and this angle is d theta. So based on the geometry, we know that this part will be r d theta. And we know that the pressure is the force divided by A, but in the question it is said that the pressure is the force divided by length here. So here, this force that is applied to this segment, this small segment, this tiny segment, is P times r d theta. R d theta is the length. So now tell me how much is the angle between the force, this force, with respect to the y-axis. It is theta. Oh, I forgot something. You might ask, okay, where should we put the origin, or where should we put the x and y components? When you see a circular part, every circular part has a center because it is part of a circle. So it's better to put the xy coordinates at that point, and x and y obviously will be, x will be in this direction and y in these directions. So we find the force at this segment and we know how much is the theta. The next part is to find the components. We have to always find the components. So as I said, we know that this is theta, so it will be PR d theta cos theta. I put negative here because it is pointing downward, and as you remember in the previous slide, the y was The y positive was upward. And this component, the x coordinate, x component will be PR d theta sine theta. So when you have a d theta, you cannot use the summation like this. You need to use the integral. And the next part, which is very important, and very important, you need to tell me for each single element, theta is varying. How actually? So how much is the theta at for these elements? If this, because we can move this element can be at any point on the beam. So if it is here, the theta will be 0. And if it is here, if I move the elements to the end point of the beam, it will be 90 degrees. So I will write here from 0 to 90 degrees, but instead of 90 degrees, you need to put pi divided by 2 because we are working with radians. And then you will copy the y components here. You don't need to put d theta. It will automatically be in the y components. So what else we have? What are the other forces that are exerted on the beam? The next one is VA, which is pointing upward. So for summation of Fy equal to 0, we just write VA. And we can also take the negative out of the integral, minus integration from 0 to pi divided by 2 PR d theta cos theta. Actually, this part should be here. It's much better. For the summation of fx, we will do the same thing. We just type here integration of all of the x component of the element from 0 to pi over 2. What else we have here? We also assume that the CA is pointing in the x positive direction. So plus this equal to 0. So minus P R d theta. I will always move d theta here first and sine theta. Why I move this theta here? Because for integral, for doing the integration, you need to make sure that the differential part is at the end. Okay, the last part. What about the moments? For the moments, you need to draw the line of action first, and then you need to find the best stop spot to find the components. If you might ask, okay, why we will not find the component at these points? Okay, remember, for the beam, we always have to find the moment at the point of the A. One of the, for example, if it is fixed at the wall at this point, you need to find it at this point. So you need to make sure that the moment of one of these components will be equal to 0. Okay, I will move this force to these points, and the moment of this y component will be equal to 0 because it is passing through A. How much is the moment arm for the x component? It is equal to r, because the radius of this circle is r. So it will be minus PR d theta cos theta. I will copy this here. I am a little lazy, I will not write it. Times r, that's it. And again, we have d theta here. You should say that, okay, theta is changing from 0 to pi over 2. And also, when you get rid of the wall, you need to put a moment. As I said, it's always better to put the positive direction in the counterclockwise. Because of this, I assume that the reaction moment is acting counterclockwise. M plus this equal to 0. Okay, another point I forgot to mention that, but when we have a beam here, remember, and we have a wall here, instead of the wall or the support, you need to put AX, AY, and the moment as a reaction forces and reaction moment. Okay, then you can find the integral, which is easy for you, I'm pretty sure. P is constant, R is constant, you can take it out, and integration of sine will be what is the integration of the sine? Negative cosine. And what about the integration of cosine? It will be sine. Okay,